To this day, I'm so conscious about doing this. Because I remember one time I did that, and then you text me and you go, I booger check.
I love that that's going to be the start of this class's video. Oh, goodness gracious. All right.
I feel so conscious. Don't be self-conscious. I think I'm sorry.
All right, I need your undivided attention as we start to talk about geometric series. All right, has anyone ever heard the word series before?
Yeah.
What is a series? All right, a set of numbers, and what am I doing to all of those numbers? Because there's a difference between a sequence and a series. So let's talk about it. All right, have we seen this notation ever in our lives before? Cool. All right, so that's the notation for the series. We're going to use it sometimes, not all the time. Sometimes we're just going to list out our terms. Now, what the difference between a sequence, which is just a list of numbers, and a series is we're going to add all of those numbers together. So we're going to be like, I'm going to take the first one, a sub 1 plus a sub 2 plus a sub 3, and I'm going to just keep going until I hit this a sub n, whatever my nth term is. But then I'm going to keep going forever. So you might have done some series before. In Algebra 2, they teach them. I don't know if you got taught them, but in Algebra 2, they do teach them. I heard they got pushed towards the end of the year a few years ago. And then in pre-cal, you talked about them as well. Now, we're almost exclusively going to be talking about infinite series. So the kind of explain it like I'm 5 version of this unit is if we add up infinitely many numbers, do we get a number or do we get something that's too big to be a number? Do we get infinity? In other words, does our series converge? We get a number. Or diverge? We don't get a number. The answer to that question is it depends, and we're going to find out like 8 or so ways to figure out how we know. So we're going to investigate a specific type of series today called geometric series, which happens to be one of the most important series that we do, but also one that you may have been exposed to earlier in your math career. Now, if you haven't seen this notation before, this is the Greek letter sigma. So sometimes you'll hear this called sigma notation or summation notation. That's not really important, just in case you're wondering what that symbol is. This in here is often called the nth term. You can think of that like a formula for finding your terms. Now, notice when I plug in, if you think of like the domain of a series, if you will, it's going to be your whole number. So we can't really graph a series the same way we graph a function because we're not plugging in things like 1/2, 0.3, whatever. We're plugging in 1, 2, 3, 4, 5, 6, all the way to infinity. How do I know where to start? This number down here. I'll just write start. All right. That could be n equals 1. It could be n equals 0. It could be n equals 17. But whatever number is down there that's where we're going to start. And this is where we end. Again, for us, that's pretty much exclusively going to be infinity. We're going to usually have an infinite number of terms, which makes our conversation a little bit interesting because I can't just sit down and add up infinitely many terms. I mean, I could, but it would be really boring. So we're really not going to do that. What we're going to try to do today is to see some patterns using partial sums. And then through the rest of the unit, we're going to get some very like rigorous proofs for how we can decide if something converges or diverges. So for the first part of the notes, we're not really doing proofs. We're going to kind of investigate, get a feel for series, and try to make up a rule for specifically geometric series. Are you ready to investigate? Cool. All right, the first type of series we're going to talk about is called an arithmetic series. The word sequence, I don't mean it. Because we're going to do a sequence of partial sums. We're going to look at arithmetic, not very long, because for our purposes, they're not going to be super interesting. Does anyone remember arithmetic sequences from, say, Algebra 2? If the answer is no, that's okay. All right, it sounds familiar. All right, let's look. There's something called a common difference between the terms. What does it look like I do to the terms each time? Add 2. So for arithmetic sequences, they're always going to be like that, where they kind of add or subtract the same number every time. So if you had to predict the next term, what would the next term in this series be? 9. Wow. All right. What we're going to do is we're going to make a list of what's called the partial sums. We're actually going to do the first 5, meaning I'm going to do the first couple, and then you're going to finish out S sub 1 through S sub 5. So this is not a rigorous proof, but we're going to try to see if we can find a pattern. So S sub 1 means I'm going to take the first 1 term and add them together. So 3. Wow. Now I'm going to take the first 2 terms and add them together. 3 plus 5 equals 8. What's S sub 3 going to look like?
5 plus 8.
3 plus 5 plus 7, or 8 plus 7, which is 15. Now, I'm going to ask you to do a couple of things. I would like you to find the S sub 4 and S sub 5, and then I want you to think about, if I took this and did infinitely many terms, where do you think it's going to go? Do it.
We're writing it down. Could we have just done the 7 if you want it out?
We probably won't ever do this again, so I'm mostly just adding all of them to be really explicit about all of it. Yeah, so I'll make sure to tell you guys today when we stop investigating and start getting the questions we would actually do.
No,
We will have some exclamation marks in there. We will have some factorials. They come back a little stronger in the next unit, but we'll have them here. Not for a while.
I kind of like these. I could do
All right, what did you guys get for the 4th partial sum?
24.
24, 5th?
35.
35. All right, so what we're going to do is we're going to actually investigate a sequence here, meaning just a list of numbers of our partial sums. And we're going to see, do we think this goes anywhere? So we're going to look at 3, 8, 15, 24, 35. All right, and I would like you to make a prediction. So we're kind of coming down here. What do you think if I took this to infinitely many terms? I can't really get there, which is why I'm using a limit. If I went to infinitely many terms, do you think I'm going to get a number? Or do you think I'm going to get something that's too big to be a number?
I think it's going to be too big.
I think it's going to be too big as well. Okay? So what that means for me is that these partial sums kind of increase without bounds. They get so big that I can't put a number on how big they're growing. What does that mean for me and this series? The series is going to diverge. Why? I didn't get a number. Nope, there is no bound to how big that sum will go. If you think kind of logically about why that's happening, I'm adding a bigger and bigger number every time, right? That's not going to do well for me trying to get a finite sum for this. I would need the terms to start getting smaller. So let's talk about other arithmetic sequences. So we talked about how arithmetic, I either add the same number every time or I subtract the same number every time. So I could have done, I could have started at 3 and gone like 3, 0, -3, -6, -9. So I subtracted 3 every time. That's another arithmetic sequence. I want you to talk with your neighbor for a second. Do you think there are any arithmetic series that do converge? We have this one that didn't. Do you think anyone where I add or subtract the same number every time to get the next term, are any of those going to converge? Talk with your neighbors for about 30 seconds.
Unless they have like it stops. I think there's
I bet this dude on my
Who said you could times? No, it's oh, you're talking that still. All right, what do you guys think? Do you think there are arithmetic series that converge?
Yes.
Which one?
If they don't have a limit of
What do you? How would I get a one that doesn't have a limit of infinity?
just make it so it's like if you're writing a problem and you just write like a 5 instead.
But how would I get if it's arithmetic? Could I get it to be 5? Elena, what do you think? I cannot hear Elena. Ma'am? No. Would it? If I did like, say the first term is like 3 and I add 0 every time. So I have 3 plus 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 3. Okay, so 0 plus 0 plus 0. That's kind of a trivial one. That I don't think the common difference of 0, I don't think that counts for arithmetic. You found a trivial example, meaning kind of a silly example. I don't think it counts if that's a good question. I don't think it counts if arithmetic if there's a common difference of 0. Thoughts, Emery? Fair. For us in this discussion, yes. So we're talking infinite series. Cap. How would we get the numbers to get smaller and smaller? All right. So if I divide, though, is that arithmetic anymore? No, I'm just adding and subtracting. You're thinking about 2 questions ahead of me. Dividing would help, though. Yeah. Good. So if we do arithmetic, we're going to get one of 2 solutions here. Either we're adding more positive numbers every time because we're getting bigger and bigger with our common difference that's positive, or if we're subtracting, these numbers are getting bigger and bigger in the negative direction. Once I add them all together, I'm going one of 2 ways. I'm going to infinity or negative infinity. So actually, no arithmetic series are going to converge. These all diverge. For us, what does that mean? In calculus, they're boring. We're not going to talk about them literally ever again. So what's a more interesting way to do this? Yeah, so kind of going back to what Nate and Kat said before, we want these terms to get smaller because if we're going to add infinitely many of something, it needs to be getting smaller if I want this to converge to a real number. So now we're going to start talking about multiplying and dividing, and things are going to get more interesting. So we're going to look at a couple examples. They're all going to be relatively similar. I will tell you again, here we're investigating. So what we're going to do in a second does not count as a rigorous proof. This is us kind of investigating what's happening. Once we get towards the end of the notes, I'll show you what counts as a proof for this stuff. So does this one look a little bit more promising? Okay. This is called a geometric series. Again, this is one that you might have talked about in Algebra 2, maybe pre-cal. What does it look like is happening every time between the terms of this series? What do you mean multiply by 2? All right, the denominator is multiplied by 2. So I could say I'm dividing by 2. What could I say I'm multiplying by? 1/2 or 0.5. So every single time I'm going and multiplying the term by 1/2, which is doing this kind of thing that you guys said would be valuable. I'm making my terms smaller so that as I'm adding them, it's getting to be a small, kind of a sum that's getting larger, but it's getting larger in a smaller way. Now, like the common difference, this is called a common ratio. And that ratio word is something we're going to talk a lot about today because it has all to do with telling whether the geometric series converges or diverges. So this one's a little bit harder to see the pattern. So we're going to write the first 10 terms of the sequence of partial sums. This is where our calculator is really going to get called into play. So if we think of S sub 1, that would just be our 3/2. I'm going to write it 1.5. Patterns with numbers are a whole lot easier to see with decimals to see if something's approaching something than if I have a giant fraction. So what I would like you guys to do is we're going to go from S sub 1 all the way to S sub 10. I want you to give me decimals. You can keep it at 3 decimal places if you want, just to be AP friendly. But I want you to use your calculator, get me some decimals, and at the end, I would like you to figure out, can you make a conclusion? Do you think the partial sums, as we take those terms to infinity, do you think you know where they go? Okay, so S sub 1 through S sub 10. If you want, when Jillian was asking how I was writing those down, remember you can take the last partial sum and just add the next term. That'll make your calculations a little bit easier if you don't want to keep typing all of those fractions. All right, take a couple minutes. I'm going to walk around. If you have any questions, let me know, but you're just adding. Yeah, Ashley. So I just put 3 halves over 4, and then the next one you should just do plus 3/8 and then plus 3/16 and then break it up.
We should do it closer.
We
could all do this.
Yeah, but it doesn't matter here. I do that one.
Well, I
Because
know.
we're gonna test where the numbers go. It's harder to get it.
So I get my
How do
You
you
are-
for.
Oh, just kidding.
Well, I don't want to, so you can go out of
I pick up Michael. I'll just give it after 0.7.
Because I was like, how did
No,
1.5
Point-
Very good episode. Yeah. Alright, I just have to ask first. I don't think we need to look. We need to. I get everyone like.
Oh, we're adding.
Good thing I
I just.
Yeah.
Oh, is he
Oh,
getting
I
it?
do guys.
That seems stupid to waste every time.
Is he getting it out? Because I was there and I was like, alright, well, I'll go for a 5.
This wasn't enough time.
How is this one here? And it's also time to process it. So kind of like the integration techniques where you have to choose the right dimensions. It's like a safari, and you have to have the right.
I'm just.
All I did is like the calculation.
Yeah.
If you want to round to 3 decimals, you're cool. Make sure I want you to add these. So for S sub 2, you should actually do 1.5 plus the 0.75. This one should be those 3 terms added together.
Wait a second, but if you do that, how are you supposed to say?
I'm sorry.
I figured this out on my
Like, it's the answer.
Yeah, if you guys just want to write the answer, that's cool. So I was just going to write the decimals. Apologies. I should have been more descriptive.
Is it never gonna get to 3?
I don't know. What do you think?
Okay, well, not the answer. So it's getting small, because you're adding, because the addition's getting smaller and smaller.
Agreed. The terms are getting smaller.
Not for real, bro.
Mhm. Yeah.
Yeah, there's always like other.
So that would be, if this was like your end term, that would be like A sub 1, A sub 2. So you're having like your end term if this was A sub 1.
How did you do it?
I don't know. I don't know if you can either of us.
How are you already there?
Y'all just copying mine. Liars.
Work smart, not hard.
Even for the middle. That's still messy. Tracy's dad was 19. His dad, and then he used the command line, but they never used it. So it's like, Trace, we're testing,
So let's talk about these terms. So it doesn't really matter if you round it or not. We're just investigating here. All right. So we're putting our little detective hat on. We're doing some investigating. Do you think you know, if you had to put money down, do you think you know, as you went to infinity, where this series is approaching, where this sum is approaching? If I had to put a number here, I would probably put 3. Now, does it have to be 3 based on the work that we've shown? No, it could be 2.999. I don't really know. It could be infinity for all I know, but it appears to approach 3. So we do want to get a little bit of a difference between an actual proof that we're going to be doing in a little bit and just our kind of investigation that supports this idea. I will tell you the answer is 3, and we're going to have a way to show that in a little bit. But it appears that these partial sums go towards 3. So do you think this series converges or diverges? All right, this series converges. And what does this 3 mean? This 3 would be the sum of the series. So if I could actually go and add up all of those infinitely many terms, they would add up to 3. So there's actually, it's a really terrible math joke, and I think it's cool, but you're not going to. It's a little spicy because it involves a bar. Yeah. Little similar. So some people like to think about this graphically. It's a little hard because we're plugging in very specific numbers. But someone made a good comparison to like a horizontal asymptote on the graph. So if I could graph all of these partial sums, it would appear kind of like a horizontal asymptote approaching 3. That's a really good comparison. The math trick that I was talking about is like, imagine infinitely many mathematicians walk into a bar. The first one, it's usually started with 1, but whatever. I'll do that one. The first mathematician orders soda. The second one orders half a soda. The third one orders a fourth of a soda. The fifth one orders an eighth of a soda. And the bartender says, stop. And he pours 2 sodas and walks away because that infinite series would add up to 2. So there you go. You can now understand an infinite series. So to put this one into context, first one orders 3/2 of a soda, next one orders 3/4 of a soda, third one orders 3/8, fourth 3/16. They would say, stop, pour 3, share it, be done. Oh no, that's the joke is like that the bartender gets the series and is like, I know what the sum's gonna be. All right, so my question then, I'm gonna let you guys talk again. My question, do you think, so remember a geometric series, there's a common ratio. There's something I multiply each term by to get to the next term. My question, do all geometric series converge? Talk to your neighbors. No. All right. Does anyone think they know? Are all geometric series going to converge? No. Why not? Oh, what if I multiply by 2 every time? Let's say my first term is 2 and I multiply by 2. 2 plus 4 plus 8 plus 16 plus 32. If I keep going, is that going to converge? No, because those numbers are getting bigger every time. That's no good. So, okay. So because we multiply by a fraction here, that was helpful. So the answer to that is not same. Some of them will. What is it going to depend on as far as our geometric series? And whole numbers or fractions for what part of this whole thing?
The bottom, the ratio.
The ratio, perfect. So it's going to definitely depend on the ratio. So just to show that to you, I'm going to show you a different one in a second, but I'm going to take a pause to talk about something that's going to come way later. One of the hardest things we learned this year has to do with how far an approximation is from an actual sum or an actual value. So we're going to stop and talk about it at different points before we get there. The actual section is called Lagrange bound for error. It's a lot. There's a ton of variables. So we're going to stop and talk about it before we get there. And we're just going to preface that and kind of prime our brains with what error means. So when I say error or sometimes remainder, what I mean is how far off is our 10th partial sum from the actual sum that we would get. So if you're thinking about this, a lot of you guys do this in like a science class. Yeah, but you might do percent error. We don't do percents in here. We're just going to talk about how far are we off. So all you're doing is taking your actual value. So in this case, we would have the number 3. This is an absolute value bar. And my approximation for my 10th partial sum was that 2.997. So our error in this case would have been 0.003. Okay. At the end of the day, we're going to be talking a lot about error at the end of our next unit. So just when we get a chance, I'm going to kind of reference it so we can get an idea of what that is before we kind of jump into the big idea. Just a throw out there question for a second. How do I make the error smaller if I'm talking about series? Go further, use more terms. All right, Nate, what's your question? Maybe. Can you try to rephrase it so I make sure? Yeah. So the end result is that for most series that we do, we can't hit infinity. So the Lagrange thing that I was just talking about is actually we're going to find an upper bound for that error. So you're going to kind of find a number that you know is definitely bigger than how far you're off is going to be the end result. It has like 3,000 variables in it. One year my notes said like, what are all these letters? Got a lot. All right, let's talk about this series right here. Is this guy still geometric? What am I multiplying by each time?
3/2.
Okay, 3/2. Let me show you 2 different ways to see that. One, I multiply by 3, and I multiply by 2. That's probably what you did. Ooh.
Oh, it tells you right there.
3 halves to the n. As I put bigger and bigger numbers of n, that's more and more 3 halves I'm multiplying by. That's going to be one of the biggest ways we're going to look at our R when we look at actual geometric series, is to locate the thing that's to the n power.
Oh, just like here it was.
Exactly. So this one up here, you might not have seen it before, but we have this, this 3 can just kind of chill. The 2 would be in the bottom to the n power, and I could put that 1 on the top. So you can see that ratio of 1/2 still. All right, let's do, I think you're going to be able to see this pattern faster. So will you find me S sub 1 through S sub 5? Again, you can just use decimals, just write the answer out. You can use 3 decimal places if you feel like just cutting it off. You're going to be able to see the pattern pretty darn quickly. So again, S sub 1 is just 1.5 for that 3 halves. The next one, you're going to want to add the first 2 terms, add the first 3 terms. If you're feeling spicy, once you found those partial sums, see if you know where the sequence of partial sums is going to approach. And then what do you think your series does? If you don't turn in your form, you're not doing outreach. No, no exceptions. 20 seconds. Yeah. I can give you your form back if you'd like to write their name on it. I can give you your form back. That's okay. Just remind me. Yes, there needs to be like a person from this building that is technically responsible for it. You could ask them. They essentially just have to send a scripted email. So it's very easy. All right, I'm gonna say the numbers that I got. 3.75, 7.125, 12.188. I started rounding. Now, if you had to put some money down, and you were a betting guy, gal, or non-binary pal, what would you put right there?
Infinity.
Yeah, I think these are getting a lot bigger as we go, right? So if you had to say what you thought the series did, yeah, you would probably say that this diverges. There isn't a sum that's going on. Why does that make sense kind of logically if you look at the terms? All right, the denominator and the numerator are getting bigger, but can you guys? All right. You're too far. Yeah, we're getting bigger every time. The terms are getting bigger. I'm adding something that's bigger and bigger and bigger. It's going to get too big. So what we're going to do in a second, then we're going to take, actually, I might just not take a break today so we can get what I want done. I'm giving you 30 minutes to just work on your problem set.
Come on, let's go.
If I get done early, then you get more time to work on your problem set. So stop whining. How about you can take a break once the 30 minutes starts? I don't care.
I like it.
Good luck on your problem set. All right. So I would like to not tell you the rule because it's cooler if you decide. So I'm going to tell you, and you're probably already starting to notice that the convergence or divergence of a geometric series has a lot to do with the ratio. So what I want you to try to do, we're going to fill out the stuff at the top in a second because that's kind of review from pre-cal or algebra 2. I want you to try to fill in these two boxes. Be as specific as you can. Consider all types of numbers that R could be. Can you tell me a statement about R that tells me when the geometric series converges and when it diverges? I'm going to give you a couple of minutes to think about it. I'm going to come around and ask you some extension questions if I see you're kind of on the right track.
Okay.
Yeah, no, if it's equal to we're still back.
So I want to know based on the ratio. This one's the ratio.
If it doesn't get smaller, it's the same size.
You're right. We're about to-
Oh, yeah.
That's what we don't.
So R is less than.
A lot of people are comparing plus or. It means it's gonna diverge. If it doesn't. You have to add them together, so you multiply by one. Extension one. Right. What about negative? They get
Then
I think we
add
got
decimal places.
No, it like.
What? What?
So like, what if I multiply by negative? That's not bigger than one.
Why, so you subtract is, oh, yeah.
I don't know where this is.
I'm happy with
All right, what do you think? Yeah, that's what it would do. So your question is like, what happens? All right, so a bunch of you are comparing the ratio to a specific number. What number were you comparing it to? 1. It looks like 1 is kind of the make or break number. So let's talk about, what did you think you could write down for diverge? People in the back hold because you're more right than the rest of the room. Yeah.
We said greater than or equal to.
All right, perfect. So let's talk about greater than or equal to 1. I'm interested in the equals part. What would a series where the ratio is equals to 1, what would that look like? Yeah, 4 plus 4 plus 4 plus 4 plus 4 plus 4 forever, but there's infinitely many 4s, so I like that you noticed that that was going to diverge. Perfect. So we've got R, I'm just putting the opposite, R is less than 1 would be here. All right, now I walked around and my extension question was, what if R is negative? What Jillian was just telling me is those terms would do what's called alternate. It's kind of like oscillating, but they would alternate in sign. So one would be positive, then negative, then positive, then negative, then positive, then negative. But do you think, yeah, kind of doing that thing. So what do you think if my ratio was like, let's say -2. So let's start with 1. 1, then -2. So 1 minus 2 plus 4 minus 8 plus 16 minus 32. What do you think that's going to do? That would be great, wouldn't it? It's going to diverge, actually. And that's because that kind of limit is not going to work out the way we want it to. So what's a way to kind of fix these statements? Absolute value. Now, you're technically right. Charlotte wrote it in a different way. What's up, Matt? That's a really interesting series. So you're talking about like -1 to the n. We're going to talk a lot about this. That's actually called an alternator, and it will be a lot of what we see in an alternating series test, which we'll get to. Technically, if you want a series to converge, you know what, I'm going to go too far into it to make this a good explanation right now. So pause that question because this term is going to come up a lot. But for right now, we're just talking about this ratio in general. So pause that question. We'll definitely answer that coming up. All right. So this absolute value is going to help a lot. Charlotte kind of wrote this bottom one. You could write that your R's need to be between -1 and 1. That's what this is achieving here. The real goal here is I want my ratio to make my number smaller every time. So what I need is smaller stuff or like bigger stuff on the bottom of my fraction. That idea of division. We need to make this guy get smaller and smaller every time. Whether the terms alternate in sign or whether they don't, we need them to be getting smaller. So eventually we're adding 0. Now, there's going to be one thing I write down that is like the one thing I needed you to remember from Algebra 2, and that is how to find the sum of a geometric series. Now, this may be blurry. It may be that you just are like, I may have seen that before. This is one thing you're just going to have to memorize. So your sum is A over 1 minus R. Has anyone seen that before? Okay. Yeah, you might have seen it for an SAT. All right, we'll draw them in like 4 classes. All right, I want to translate this a little bit. A is not just like any old term. This is the specific first term. We have to be careful in this class because while most of your geometric series in like algebra 2 started at n equals 0, and you can see if you put that in there, this is the A. Our A could be different because sometimes I'll start the series at like 5. So make sure you're plugging whatever number is in on the bottom. You're going to plug that in to get your first term. What do you think the R stands for? The ratio. Now, there are certain times when this is valid to use to find the sum. 2 things have to be true. 1, we have to have infinitely many terms. If we're using this to find the sum of like the first 10 terms, you're doing it wrong because if you had 10 terms, you should just add them together. All right. Also, your series does need to converge. One of my biggest pet peeves is I'll put blanks for people to find sums, whether the series converges or diverges, and people will tell me the series diverges and then try to tell me what the sum is. The point of saying that something diverges is it doesn't have a sum, it's too big. But if you try to use this formula, it'll give you a number. That number will just be wrong. So to put this more specifically for geometric, that ratio absolute value has to be less than 1. Okay, so if that's true, I can use A over 1 minus R. Yes, ma'am.
What are like plugging like R into like
Uh-huh.
do we have to put it in that?
No. So when we put it in there, that's a great question. If we put it in there, if the ratio was negative, you'd have like 1, and that minus would turn into a plus for that negative. We'll practice with it. I promise. I promise. I promise. All right. So if you have not been listening at all today, now is the time to start. So the next 2 questions are what we would actually be doing if we were doing these questions for real. So these are going to be the directions, kind of like it. This chapter, minus like the massive amount of algebra skills you needed. This chapter kind of follows along with the integration techniques chapter, where it's a lot about choices and it's a lot about applying the right method with very simple directions. So our directions are going to be determine whether the series converges or diverges. Going back to what I was talking about at the very beginning of class today, you being able to tell me if this converges or diverges is fine, but we're crafting an argument. So all of the things I write down other than the word converge or diverge are kind of the important part. So let me show you what we're doing. All right, let's start here. I'm going to rewrite this one kind of like me and Nazi were talking about earlier. I'm going to pull the 3 forward, keep this 2 in the denominator, use a 1 as a placeholder so I can really easily see what I think R is. Because for geometric series, it's all about the ratio. So usually when we're doing these convergence and divergence tests, we're going to be identifying some number. In this case, it's going to be R. What is R for this series? 1/2. The next question I'm going to ask you is, why do I care about that number? Okay. In this case, what I mean specifically when I say, why do I care about that number? There's usually going to be some sort of comparison. So for here, the absolute value of that R, which is 1/2, is less than 1. So a lot of the times your test, your series convergence or divergence test is going to produce a number. You need to tell me, what do I compare it to? Why do I care? There's going to be lots of conclusions. We need to be able to write those conclusions. Now, because we got something that was less than 1 for our ratio when we absolute value, this series is going to converge. And I know how much you guys love to write things down. So we're going to write what test we use. Then this is the geometric series test. You may be wondering to yourself, how many tests are we going to do? About 8. There will be some that we can use abbreviations on. I would love to see at least the whole word geometric here. I cut someone else's question off. Hannah? Yes, and I will have a flow chart for you. There's going to be a lot, and we're going to kind of like the integration techniques one. We're going to be practicing with which test goes with which thing. So like geometric, these are really good when we see something to the n power kind of isolated like this. All right, Yes, ma'am.
If it didn't just say like determine whether we were in the heavily.
We're gonna do that in a second. Yep. Actually, let's do it now. So Ashley was asking, what if I asked you to find the sum? Because geometric series, they're one of the few that we're actually going to be able to find the sum. I know I have 1 minus the ratio was 1/2 on the bottom. What goes on the top of this fraction? Neither of those numbers. The first term. All right. What number am I plugging in to find the first term? I'm plugging in the n equals 1, which is going to give me 3/2. So just be careful. A lot of the times in algebra 2, you just pull this number because your series started at 0. We're going to make sure we plug in that bottom number to find our first term. We could simplify that. Let's do it because these were the terms that we were adding up. So 1 minus 1/2 is 1/2. That's 3/2 times 2/1. This number look familiar? Remember how all of those terms looked like they were approaching 3? They did. All right. Let's do another one of these proofs again. So we're looking at this series. We want to know converge or diverge. We look at it. We see it looks like something to the end. We're thinking geometric. So what is R? 3/2. Why do I care? The ratio is greater than equal to 1. So this is going to diverge by geometric series test. Again, kind of going back to some of the questions we've done throughout the year. You are crafting an argument. Pretend you're a lawyer. You are presenting all of the facts. You are assuming the person reading it is dumb as a bag of bricks. You've got to make sure you lay it all out. So even though you can see that 3/2 is definitely bigger than 1, I'm reading your paper. I'm dumb. I don't know why I care about the number 3/2. You got to tell me. Could I find the sum for this one? No, it diverges. Okay, but if you try to do it, you would get a number. It would be negative, which would be weird because you're adding up positive terms. So you got to make sure if it diverges, we don't get a sum. Nope. If I tell you to. Yeah, Michaela. Yeah. So do you notice how this 3 does not have like an n power on it at all? So I pulled that 3 out front and I took the 2 from the bottom and put it inside here to the n power. Since that 2 was on the bottom, I needed kind of a placeholder for the top, so I put a 1 up there. I think dividing by 2 over and over, same thing as multiplying by 1/2 over and over. Here, if I wrote this one out separately, I would have like 3 to the n over 2 to the n, so both of those would have an n power on them. So it's kind of the difference between those 3s. Absolutely.
So
Thanks for
yeah.
Yeah, you could do 1 to the power of n. 1 if you multiply infinity ones, you get 1. All right. Geometric series are, surprisingly enough, one of the very few series where we actually are able to find a sum. A lot of the times we're just going to be able to be like, oh, it converges. You can find a sum. Good luck. Don't know what it is, which is a little frustrating. But that means that geometric are a good place to go to get some multiple choice questions. So I'm going to show you a couple until my timer goes off. This one's actually off an AP test. It's really cute. So we have a geometric series. We are guaranteed, based on this statement here, that all of our terms are positive, meaning that our ratio also has to be positive. We can't alternate. They tell me my first term is 108, and they tell me my third term is 12. They ask me for the value of this. Does anyone know what singular word they are asking for here? The sum. Yeah, it's just a very, very scary way to say, can you add all these numbers together for me? They're talking geometric. What do you think we're going to need to find? The ratio. So I think it would be helpful if we could find a sub 2, maybe. How do you get from 108 down to 12? Divide by 9. What could we multiply by? All right. let's say I want to do that in 2 steps instead. Times 1/3, times 1/3. Let's check. What's 108 times 1/3? 36 is times another third. We get 12. All right, so let's find our sum. What goes on the top of our sum formula? First term, which is? All right, and 1 minus 1/3. If you multiply all of this out, 162. All right, last one I want to talk about. Maybe, maybe not. I'd probably, actually, this one was a real one, so I don't remember. Probably not, to be quite honest. Maybe though, because they don't give you that much information to work with, so maybe. All right, I want to do, yeah, would love to. Yeah. All right, so I want to talk about a couple of these before we leave. And by that, before I mean we leave the lesson part of this. Is that a bell? Did you? You hear it? But it sounded weak and terrible? All right, let's talk about, I'm going to try to do A, C, and D. That's a little optimistic, but here we go. Actually, let's just talk about D. Does this one look like a geometric series?
Yeah.
Kinda? A little bit. The vibe that it's giving me is I see these n powers here. Let's use some exponent rules. Make it look like a geometric series. All right, how do we get addition of exponents that's like in the bottom? How do I get that? Think less. All right, Matt, can you say that louder? Yeah, multiplying the like bases. So would you agree the bottom, sorry, that was a really poorly phrased question. Matt, thanks for reading my mind about what I wanted. 5 to the n times 5 squared. Would you agree that's 5 to the n plus 2?
Yes.
All right, how do you think I could get something to the n power on the top?
So you have to raise it to the power of n.
So I heard Nate say squared. I'm hoping he meant this. Yeah? Nice, Nate. All right, do you guys agree, though, that 2 squared to the n, I would multiply those exponents? So why am I doing this? What I want to do is I want to get the geometric series have like a number to the n power. So I'm going to take this number and make it to the n power. So I have 2 squared is 4 over 5, all to the n power. I'm going to finish this problem. What am I missing? Then finish the problem faster. What am I missing? 1/25. All right, what's R? 4/5. Why do I care? So this
Less than 1.
converges. Can I find the sum?
Yes.
All right, my sum, 1 minus 4/5, is the first term 1/25. No, what do I have to plug in to find the first term? 1. So I'm going to do 1/25 times 4/5. 4 over 4 over 125. You're feeling fancy. All right, I'm going to just tell you the reason I did this question only out of these 4. I love this question. You will see a question like this again. Star it. You're going to see one like it on the AP test probably. You're definitely going to see one like it on the test that I give. Yeah, so the exponent rules are really cool, but all of that stuff to the n power really reminded me of geometric. All right, so we may revisit the top 3 again someday, but for right now, guess what? It's problem set time. I do have an answer key if you would like to check anything. Just to give you some dates. Problem set, due next class. That is Tuesday. Next class. Next class. It is so soon, but it's actually not that long of a problem set. I would like to put out there, after you set up your integral, You can use a calculator. You don't have to do any of these by hand if you don't want to. All right? Test Thursday. Partner, Desmond's help. Check?
On the test, can we use a calculator?
Most likely yes.
Yeah.
Like, like simpletons.
They're not.
Chuck, get over here to talk about Rock Slide.
They're like, I am. Probably like, exploded.
Check it. Rock playing Candy Crush. Okay, hold on. I don't know what this is.
Sunflower.
No, we can talk about flower now. Oh, there.
What's up, Sean?
Copy of.
Sit down. Let's talk about it for a couple of minutes.
Like, never mind.
Okay. I wrote the same thing as you.
Hello. What?
You want to know what you go for?
Oh, tell it.
I didn't put mine out.
Yeah.
So how do you tell the shape if it's just like this?
You look at the bounds.
That one's fire.
Wait, it's a diamond.
Curvy triangle.
I get tired sometimes.
So do you have to do the two intervals like we did?
You have one consistent function that's on top, one consistent function that's on bottom. We're just going from 0 to 2. Oh, you left it in pi? Darn it. No, you're fine. I just don't know the answer in terms of pi. Oh, let me stop recording. Bye.